Namaskaram. In this session, we will discuss triple integration in spherical coordinate system, the solution of last formula. Okay. In Cartesian coordinate system, we locate a point in 3D using x, y, z, three coordinates. Okay. Similarly, in spherical coordinate system, we can locate a point using these three values. That is rho, phi, and theta. And what is rho? Rho is the distance from origin to that point. So this distance is rho, right? And the next one is phi. Phi is the angle measured from positive z-axis to this line segment. So this angle is phi. Phi is the angle measured from positive z-axis to this line segment. Okay, so that is phi. And one more thing is theta. Theta is similar to our polar system or cylindrical system. You take the projection to xy plane, then you consider this line segment, then angle measured from positive x-axis is theta. Okay, using these three values, you can locate every point in space. And this is the relation between Cartesian coordinate system and spherical coordinate system. Okay. Okay, in the case of Cartesian coordinate system, we evaluate the triple integral. First, we divide the solid G using planes parallel to coordinates planes. That means x equal to constants, y is equal to some constants, and z is equal to some constants. Okay, so then we divide the given region into small cuboids using the planes x equal to constant, y is equal to constant, and z equal to constant. Similar to this, here we divide the solid using phi equal to constant, rho equal to constant, phi equal to constant, and theta equal to constant. Okay, then next we are going to analyze what is phi equal to constant, what is theta, what is rho equal to constant, and what is phi equal to constant, and what is theta equal to constant in spherical coordinate system, or what is the geometry of these things. In Cartesian coordinate system, we know x equal to 7 means it's a plane. Clear? X equal to 7 is a plane. Similarly, y equal to 5, that is also a plane. Z is equal to 6, that is also a plane. Okay. Similarly, what is the geometry of rho equal to constant, phi equal to constant, and theta equal to constant? Okay, first we consider rho equal to constant. What is the geometry of rho equal to constant? For example, we consider rho equal to 3. Then rho means this distance between the point and origin, that is rho. So rho equal to constant means, suppose this distance is 3, then for this point its rho is 3. Then what about a point at this distance? Suppose this is same as 3. Okay, then suppose this distance is 3. Then what is the totality of all such points? Okay, all such points is a sphere. Clear? So rho equal to constant is always a sphere. Next we have to analyze what is phi equal to constant. Okay, so to analyze phi is equal to constant, I'm going to consider a particular equation phi equal to pi by 4. So what is the totality of all points satisfying this condition, or what is the geometry? So we know phi is the angle from positive z-axis to this line segment. Okay, suppose this point satisfies this condition, suppose this angle is pi by 4. Then what about all such points? Then all the points lying on this line satisfy the same condition. Here, suppose you consider a point here, then their angle is same as pi by 4. And not only in this line segment, what about whole this 2 pi radius? Suppose you can take a point here. Suppose this angle is again pi by 4. Then this point also belongs to the collection. Okay, so set of all points belongs to phi equal to pi by 4 forms a cone, right? A cone like this. And one more thing, what is the range of this phi? Phi is the angle measured from positive z-axis to that point. Okay, so the angle is maximum like this up to here. So suppose point is here, then we measure like this. Okay, so its maximum value is pi. So phi is between 0 to pi. Okay. Okay, last one is theta equal to constant. For example, we consider theta equal to pi by 6. So we have to identify what is the geometry of those all points satisfying this condition. Okay. For example, this angle is pi by 6. Suppose this angle is pi by 4, pi by 6. That means, suppose a point is here, then you take the projection, then this angle is pi by 6. So you think about all the planes, all the points lying on a half plane like this. Then whatever be the point, its projection is on the same line. So angle is again pi by 6. Okay. So set of all points satisfying this condition is a half plane like this. So now we are ready to identify a spherical wedge. The spherical wedge is bounded by rho equal to constants, phi equal to constants, and theta equal to constant. Okay. So in this example, so in this figure, first we consider rho equal to rho 1. So rho equal to rho 1 is a sphere like this. So this green area from that sphere. Next one, rho equal to rho 2. That is another big sphere. Another big sphere. We assume that rho 1 is less than rho 2. Okay. So these green patches given by these two spheres. Okay. Next we consider phi equal to constant. We know that phi equal to constant represents right circular cones. Okay. So this orange shaded regions given by phi equal to phi 1 and phi equal to phi 2. Okay. Both from the right circular cones. The part of a cone like this. Okay. And this is the part of a cone like this. Got it? And one more thing is theta equal to theta 1. Theta equal to theta 1 is a half plane like this, and this yellow region, and theta equal to theta 2 is another half plane, that is another yellow region. And these type of solids, this type of solid is called a spherical wedge. Okay, so this is our basic volume unit in spherical coordinate system. So next, what is our procedure of triple integration? Yes. Suppose we have to integrate this function. Function is in terms of rho, theta, and phi over a solid G. Then, as similar to our previous cases, that means in Cartesian system and cylindrical system, we divide this region as small spherical wedges. Okay. Then we take the sum and take the limit. That is a procedure. So sum. Okay. Okay, then to compute this integral, we have to identify the volume delta Vk. Delta Vk is the volume of the kth spherical wedge. Okay, so the volume of the kth spherical wedge, we can show that this delta Vk equal to rho k star square and sine phi k, delta rho k, delta phi k, and delta theta k. And the proof of this delta Vk is beyond the scope of our syllabus, so I just leave the proof. Anyway, this is possible. Okay, so once delta Vk like this, then we can write the our sum. Yes, so if delta Vk is like this, then as similar to our previous cases, what about this triple integral? This is equal to, yes, this rho k become rho, sorry, there is a square is there, so this is become rho square and sine phi, and delta rho k become d rho, this is d phi and d theta. Okay, so this is the idea of triple integral in spherical coordinates. So we can write this triple integral of g dv as triple integral appropriate limits of rho, theta, and phi, and rho square sine phi d rho d phi d theta. Okay. Okay, consider a problem. Use spherical coordinates to find the volume of the solid G bounded above by the sphere x square plus y square plus z square equal to 16 and below by the cone z is equal to square root of x square plus y square. Okay, so its geometry is like this. There is a cone, that is z is equal to square root of x square plus y square, and its upper bound is from the sphere x square plus y square plus z square equal to 16. Okay, we have to set up a triple integral in spherical coordinates. Okay, we know that volume is equal to triple integral over g 1 dv. Okay, so we have to convert this integral in spherical coordinate system. So in spherical coordinate system, what about dv? Yes, our dv become rho square sine phi d rho d phi d theta. So next we have to identify the limits of rho and phi and theta. And to cover this solid, what is the range of rho? Rho should varying from this point to our sphere. Okay, always varying from 0 to this sphere. And what is the equation of this sphere? In spherical coordinate system, we know that x equal to rho sine phi cos theta, y is equal to rho sine phi sine theta, z is equal to rho cos phi. Okay, it is easy to verify that x square plus y square plus z square satisfies the condition rho square. Okay, so what about our equation of this sphere? So here this becomes rho square. So rho square equal to 16. This implies rho equal to 4 because rho is always positive. It is a distance from origin to that point. Okay. So equation of this green sphere is rho equal to 4. So it is clear that our rho should varying from 0 to this point. That means 0 to 4. So this is the variation of rho. Next we have to identify the variation of phi. Okay, to identify the range of phi, we have to find equation of this cone in terms of spherical coordinate system. So to find the equation of the cone, what is z? We know z is equal to rho cos phi, and you can substitute x and y from its spherical coordinate system. So this become, okay, solving this equation, what is z? Z is equal to rho cos phi, that is equal to square root of x is rho sine phi cos theta, so there is a square. Similarly, this is our y square. Then here rho square sine phi is common, you can take outside. So rho square sine square phi into cos square theta plus sine square theta, that is 1. So again you can take the positive square root, that is rho sine phi, because sine phi is positive. What about sine, if this is the graph of sine theta or sine phi, 0 to pi. In 0 to pi, sine phi is always positive. That's why its square root is again sine phi. We consider only positive square root. Of course, rho is already positive. Then you can simplify. This is sine theta by sine phi by cos phi is equal to tan phi. Tan phi equal to 1. So tan phi equal to 1 implies phi equal to pi by 4. Okay, because phi is only varying from 0 to pi by 4. Clear? And it is clear that here this angle, that is our phi, angle is less than pi by 2. Okay, so in this interval it has only one solution, that is pi by 4. Okay, anyway, phi equal to pi by 4 is the equation of this cone in spherical system. Okay, now we are ready to write the limit of phi, because phi is varying from this point to this point. That means its variation from 0 to pi by 4. So this is 0 to pi by 4. Then to cover this entire region, what about theta? Theta is the projection of any point from xy plane. Then you take the angle from positive x-axis. This is our theta. So to cover this entire region, theta should varying from this point to this point. That means 0 to 2 pi. So variation of theta is 0 to 2 pi. So now this is setup of this triple integral in spherical coordinates. Now you can integrate. So this become the first one is integration with respect to rho. So this is rho cube by 3 and upper limit and lower limit and upper limit 0 to 4. Next we substitute this upper limit and lower limit for rho. So this become, so when rho equal to 4, this is 64 by 3. When rho equal to 0, time is 0. So next you can integrate this with respect to phi. So 64 by 3 is constant, you can take outside. So sine phi become minus cos phi 0 to pi by 4. Okay, when theta equal phi equal to pi by 4, this is 1 by root 2. So minus 1 by root 2 minus, when phi equal to 0, this become minus 1. Okay, so this become, so yes, this become actually 1 minus 1 by root 2. You can take outside constant. So 0 to 2 pi d theta, that is theta 0 to 2 pi. When theta equal to 2 pi, this become like this. Then again you can expand this 2 inside this, you can multiply this 2 with this inside the bracket. So this become 2 minus 2 by root 2, that is root 2. This become 2 minus root 2. Yes, ultimately your answer is 64 pi by 3, and 2 into this term is 2 minus root 2. Okay. Okay, next problem. Use spherical coordinates to evaluate triple integral over G. Let's go into square root of x square plus y square plus z square dv, where G is the, sorry, this is G is the solid bounded above by the sphere x square plus y square plus z square equal to 4 and below by xy plane. Okay, first you have to identify the geometry. Okay, its geometry is very easy because we know that this is a sphere. So bounded above by the sphere and below by xy plane. That means our z equal to 0. So below by z equal to 0, and we know that what is the upper hemisphere equation of the upper hemisphere, that is equal to z is equal to positive square root of 4 minus x square minus y square. Clear? Anyway, the problem is clear. So we have to set up this integral in terms of spherical coordinate system. So what is z square? We know that yes, z is equal to rho cos phi. So this become rho square cos square phi. And what about x square plus y square plus z square? Yes, we know that that is rho square. So its positive square root means 1 rho. Okay, rho is there. And what about dv? Yes, that is rho square sine phi d rho d phi d theta. So one rho square is here, one rho is here, one rho square is there. The total rho raised to 5. Okay, next you have to identify the range of rho, phi and theta. And it is clear that rho is varying from this point to up to sphere. What is the equation of the sphere? X square plus y square plus z square equal to 4. And that means rho square equal to 4. Okay, so what is rho? Rho equal to 2. So rho is varying from 0 to 2. Clear? So here the rho is varying from 0 to 2. The next one phi. And to cover the solid, we have to integrate over the solid. Okay. To cover the solid, phi should varying from this 0 to up to here. In any direction, 0 to up to this one. That means 0 to pi by 2. Clear? So phi is varying from 0 to yes, sorry, 0 to pi by 2. And last one theta. To cover this solid, what about theta? Theta should varying from yes, theta is varying from the full circle. That means theta is varying from 0 to 2 pi. So this is the setup of this triple integral in spherical coordinates. Okay. Okay, so this becomes 0 to 2 pi. All the limits are same. And this is rho raised to 5 cos square phi sin phi like this. So first we have to integrate with respect to rho. Okay, this is rho raised to 6, rho raised to 6 by 6. When rho equal to 2, this becomes 2 raised to 6 by 6. And its simplification becomes 32 by 3. And rho equal to 0, the term is 0. So this become, so that 32 by 3 is constant, you can take outside. So integration like this. Then you can integrate this by a simple substitution. For example, if you substitute some u equal to cos phi, then what about du? So u equal to cos phi, then du equal to minus sin phi d phi. So this integration become this when this become minus cos phi is u, so this become u square. And what about sin phi d phi? That is minus du. That's why there is a minus sign. And what about the limits? When phi equal to 0, u equal to cos 0, cos 0 is 1. When phi equal to pi by 2, cos pi by 2 is 0. That's why this is 1 to 0. Okay. Then you can change the order of integration, or you can directly integrate, no problem. Yes, minus sign is take outside. So u square become u cube by 3, 1 to 0. And when u equal to 0, term is 0. Minus when u equal to 1, this is 1 by 3, minus 1 by 3. And so this minus 1 by 3 is a constant, you can take outside. So this minus minus become plus. So 32 by 9. Yes, this become 0 to 32 by 9, 0 to 2 pi d theta. Then that is theta, integration of integral of 1 d theta, that is theta, 0 to 2 pi. When theta equal to 2 pi, that is 2 pi. When theta equal to 0, term is 0. So ultimately this become 64 pi by 9. Okay. Yes. So this is your homework. Thank you.